Hi, everyone. My name is Jennifer. Thank you so much for the introduction. I'm so excited to be here, and I'm so excited to be talking to you guys about building IMU-based gesture recognition. So yeah, a little bit more information about me. Professionally, I'm a software engineer and hardware prototyper, and I love sensors. And I'm so excited to tell you why I love sensors so much. I've worked with sensors on phones. I've worked with sensors on wearables. I've worked with sensors on robots, and I also did a stint at an observatory. So lots and lots of sensors. My contact info is there if you're interested. Cool, so before I get into the meat of this presentation, a lot of people have helped me with my Halloween costume. So all the people listed here, whether it's working on the presentation or my friend hand sewed this costume robe, and also please go vote. Cool. So this year during Halloween, I needed to come up with a costume. And every year for Halloween, I like cosplaying as different characters. So I've been like a minion, I've been Hero from Big Hero 6, I've been this girl Kirisu from this anime I really like called Steins Gate. And so this year I wanted to do Harry Potter. And I was thinking, well, what can I do that's really cool with a Harry Potter costume? Well, when I was a kid, back in 2001, there was this Harry Potter and the Sorcerers Stone PC game that came out. And, you know, it's very much like 2001 graphics, but I love this game so much. And one of the reasons I love this game is you, like, run around and you get to, like, wave your wand at people and, like, well, not at people, but you get to wave your wand, and it's kind of like you're in this magical world. So I was like, well, why not, like, try to build a wand that can do some spells? So specifically in the game, there are two spells that you learn very early on. One is Wingardium Leviosa. I'm just going to call it Wingardium in this presentation. These are what the spells do in the game. Obviously, I didn't implement levitation. Flipendo is kind of your bread and butter spell in the game. You kind of use it at everything all the time. It's great. So I was like, okay, let me build a wand that can do these two spells. And the final product is right here. All the code is up on GitHub, and like, feel free to talk to me later about the magic wand that I built. Cool. So once I was like, I want to come build this thing, it was like, how do I start building this gesture recognition project? So the steps that I took was I first had to define and scope the problem. Then I had to propose a machine learning model or algorithm to actually run on my wand. Then I had to collect data. Then I took this data and I had to train my machine learning model and kind of iterate until it kind of got to a good enough quality that I was happy with. And then finally I had to productionize it, move the code, put it on the magic wand, and actually like make it run in real life. So cool. And my talk today is about kind of how to build this on a magic wand, but knowing how to do machine learning on a portable Linux device, knowing how to do machine learning on sensor data really opens your world to like all these really cool hacks. Like if you know pyrotechnics, this guy built these like fire-bending gloves, which I think are super cool. But you can also use this to like steal ATM pens if someone is wearing a smartwatch, or like control music. This is like basically Frofro, and she does these like awesome music performances where she uses this gesture recognition glove system. Anywho, there's a lot of cool stuff that you can do using IMUs and machine learning. Cool. So without further ado, let's talk about how this algorithm is actually going to work when it's done. So the basic machine algorithm, like learning algorithm, kind of looks like this. So first you're going to sample some sensor data. From that data, you're going to generate features. So what these features are is, a feature is basically a summary of the sensor data that you've sampled. So for example, if you've sampled 100 data points, one feature that you might want is like a mean or a median or the range. So those are examples of features. You take these features and you dump them in your machine learning algorithm that you've magically created. And from this machine learning algorithm, it gives you a result. You want to do some cleaning, some post-processing on the result, and then you do whatever output that you'd like, whether that's like shooting fire or like casting magic or like stealing ATM PIN numbers. Cool. So let's talk a little bit more about like the sensor data aspect portion. So here we see a graph, and this is a sample graph of sensor data. So the x-axis is time. As you go along like this graph, time is going forward in the future, and you can just ignore the y-axis. Just pretend this is sensor data. So what your algorithm is doing is that box is like a time window. So you look at the sensor data in that time window, and you dump it in your machine learning algorithm, and you're like, is there a gesture here? And it's like, no. And you're like, okay, is there a gesture here? No. And then you just keep doing this until you get to here. This is kind of interesting. You dump it into your machine learning algorithm, and it's like, yes, there is a gesture here. Awesome. And you can like do your magic spell. Your algorithm, this is a continuous machine learning algorithm, so it just kind of runs all the time. And so yeah, for this one, like no gesture, and you just keep going. Cool. So let's dive a little bit into how we get that going. So first, let's start defining and scoping the problem. So when I start a gesture recognition project or a machine learning and IMU type project, there are some basic questions that I start off having to answer. The first question is, what are your resources? This is time, this is money, this is engineering manpower. For me, like, I wanted to build a Halloween costume. I came up with this idea maybe a month before Halloween, and I'm one person, so I was like, okay, let's see. The resources are me as an engineer. I have 1 month, so a few evenings and weekends, and like, in terms of money spend, like, ideally as little as possible, but ideally under $200. Cool. Next, like, who, when, and where will this be used? Again, it's me. It's going to be used for one night on Halloween, and it's going to be used outdoors in my neighborhood. And you'll find out that choosing this and scoping it narrowly is very, very important. Next, what are your power, latency, and memory requirements? So one of the things that happens when you're doing machine learning on an embedded system is often you have to make this trade-off between memory efficiency, accuracy, and real-time fast detection, which is latency. And so you're like, which one doesn't matter? And how can I like get more like of all the things? And like typically to do this, like you just have to spend more money. Fortunately for this project, I'm like, like what I need to do is just ship as fast as possible before Halloween. So I'm like, I'm just gonna ignore this because I probably won't even get this far. So cool. So in terms of power, latency, and memory requirements, I'm like, I'm not going to worry about it for now. I just need to ship fast. And finally, in the same light, how do I know when my like model is good enough? How do I know when my algorithm is accurate enough? Well, it's when Halloween happens, when the kids are happy, like the standards aren't super high. It's like, okay, I really like time-boxed projects. Cool, now that we've answered those questions, let's start defining and scoping the hardware that we're going to be using. So I know that I want to detect a gesture, and how do I know what sensors I want to try using? So let me take a look at like some options. So first, like, do I want to like use a camera? Well, we look at the problem that I defined, and we're like, well, I'm going to be using it on Halloween evening. It's probably going to be pretty dark. I'm probably not going to want to use a camera. Okay, do I want to use like IR or like wireless Bluetooth beacons for whatever reason? Well, we look at our problem statement and we're like, I'm going to be walking around my neighborhood. I probably don't want to plant these beacons like all over my neighborhood in my neighbor's bushes. So probably not. Next, do I want to do like sonar or audio? And there's really, really cool gesture recognition that you can do using sonar and audio. Like definitely talk to me about it if you're interested in it. But it requires a lot of fine tuning. It's still a little bit earlier on. So, and furthermore, I'll be walking around outside. So the environment's just going to be a little bit too noisy walking around. Next, do I do like magic E&M sensing? This kind of gesture recognition is super, super cool. Like there's research going on where you use just like Wi-Fi hotspots and you look at the shadow that's cast as people walk by to like count the number of people, or you can start like scanning through walls. It's like super, super exciting. Unfortunately, it's like in academic research right now, and I'm not an academic, I'm not a grad student, so I am not going to do this. And finally, IMUs, you saw it in the title, like, yes. So IMU stands for Initial Measurement Unit, and I'm going to tell you a little bit more about them. Yes. So an IMU is this little device. It's pretty great because you can just like go on like your favorite electronics website and buy it for super cheap. You can talk to it, this particular chip I got, you can talk to it over UART or I2C, and it gives you a really nice orientation. So an IMU is just a nice package that gives you accelerometer, gyroscope, and magnetometer over 3 different axes. So it'll give you like your Z acceleration, it'll give you your Y acceleration, it'll give you your X acceleration. So like accelerometer is like if you move this way. Gyroscope is like if you, it measures the twistiness of what you're, anyhow, it measures the twistiness of what you're doing. And magnetometer is, your magnetometer is finally just your bread and butter compass. So if you want to like spin in a circle, like you can get that. Cool, so we know that we want to use an IMU, awesome, okay. Let's figure out what kind of hardware we want to use. What is the basic system that we want to build? So this is a Linux-based project, and I wanted it to be as cheap as possible, and the nice constraint that I had is I also need to make it look nice, so I can like hold it, and if I use like a normal size Raspberry Pi or machine, I'm gonna have this huge thing sticking out of this wand. So I use this BNO055. It's a super cheap like IMU that you can purchase. I connected up to this Raspberry Pi Zero, plus the W has networking, which is nice. They just talk over UART. And then I attach this Raspberry Pi to a phone battery, and finally a USB audio speaker. Cool, and finally I glue this all to a Cosplay Wand. And you can see like the design right here. This is the wand. This is the battery, your Raspberry Pi is right here, and I actually have the IMU kind of on top. So this is kind of a cross section. And finally, like this nice wire will actually go up your sleeve so people don't know that it's there. Cool. And this is an up-close image. You can see like the Raspberry Pi and the IMU connected to everything right there. Cool. So this is the basic architecture. We have a Raspberry Pi Zero, glued to a wand, and we're going to be building on an embedded Linux-based system. This also means that we're going to be making the trade-off that because it's embedded Linux, we don't really have a nice real-time system. Our sampling rate isn't going to be super consistent, but you know, you can't have everything. Cool, so now that we've defined and scoped the problem, let's talk a little bit about like what sort of machine learning model we want to use, what kind of algorithm we want to use. And so we have a few options, so each column is one of the options. And the basic trade-off that you want to make is how much domain knowledge you need in order to be successful, how much data you think that you'll need in order to make sure your algorithm works really well, and finally, is it going to be easy to debug? Because we always take a lot more time debugging than we expect. So our first category is deep learning. Now this is like the super hot thing that lots of people are excited about. And why are people excited about it? Like you don't need a lot of domain knowledge. So you can finally like do algorithms on like text and natural language understanding without being a linguist. Unfortunately for deep learning, you need a lot of data to make it work. And it's really hard to debug because it's kind of this like magic thing that people use. Your next option is your like traditional like engineering degree signal processing. So in order to make this work, you need a lot of domain knowledge because you're basically going to look at the gestures that come out and you're going to be like, what kind of like signals would it look like and how do I like capture this in a signal processing algorithm? The trade-off is like lots of domain knowledge, but you don't need a lot of data and it's much easier to debug because you're like writing the algorithm from scratch. And like, I'm in like neither of these buckets, right? I have like about a month before Halloween. I don't have time to collect tons of data. I'm just one person. And like, I don't have a lot of like signal processing experience, like super specialized to the point where I'm going to tune these very deeply. So the third approach that I actually took on this project is traditional machine learning. So this was like machine learning that people used before everyone was super excited over deep learning. And the nice thing is you need some domain knowledge, you need some data, and like it's kind of easy-ish to debug. So it's actually a really good way to get started when you're starting to hack your own project and you don't have time to collect tons of data. Often what happens with this kind of project is I guess this is if you want to build a commercial product, you'll use a traditional machine learning algorithm to build your MVP. So your minimum viable product, you'll ship it, you'll get it out to the hands of users, and once you have these users, you have a lot of people who will collect data for you. So hooray, more users, more data, and now that you have more data, you can switch over to using deep learning. Cool. And now that I've kind of taken a look at like what my approach is, I need to choose the software that I want to use. So what language do I use? Python. What numerical libraries do I use? I use pandas and NumPy. So if you're learning Python, it's really good to learn NumPy. If you're learning Python like pandas, there's definitely a learning curve to pandas, but it's super awesome. I think it's like worth it. What data notebook am I going to use to like visualize all the sensor data that I'm going to? So I use Jupyter Notebook for this. It's like the de facto thing that a lot of data scientists use. Highly recommend it. For data visualization, I use this thing called Plotly. It's pretty good. I like it. And finally, what machine learning library I'm going to use? I use scikit-learn for this project. There's really good documentation for scikit-learn. I highly recommend using it. Yeah, there's it's just so widely used that it's really easy to kind of get started using scikit-learn. And to show you how easy it is, I've decided I want to use traditional machine learning, but traditional machine learning is still like a bucket of models. And you're like, typically, if you're at a university, you'll take a whole class to like understand all the models so you know which one to choose. But fortunately, if you're using scikit-learn, there's this handy-dandy flowchart that helps you choose which model you want to, oh boy. There's this flowchart that'll help you choose what you want to do. So first you start, and the first question is, do you have greater than 50 samples? And you can see if you don't, like, the answer is to get more data. So yes, we do have greater than 50 samples. The next question is, are we predicting a category? So for us, the categories we're trying to predict is there a Wingardium spell? Is there no gesture, or is there a flipendo spell? So there is a category where this is a classification problem. So cool. And the next question is, do you have labeled data? So I'm going to be collecting all of this data myself, and when I collect the data, I will be like, yes, there is a gesture here. No, there is a gesture here. And so yes, there will be labeled data. So now we've ended up in this like really nice bubble. It's called classification. So if you like talk machine learning to other people, you can be like, oh, I trained a machine learning classification classifier. The next question is, do we have less than 100K samples? Yes, because it's just me and we only have a month. And hooray, we've landed in a model. It suggests using linear SVC, so we're like, okay, let's use that. Okay, now that we've chosen our model and we've chosen like what algorithm we want to use, the next step is to collect data. Cool, so data collection is actually a lot of machine learning. And some of the questions that you want to answer for yourself when you start on data collection is how much data do you need? And if you need a lot of data, one of the things you might want to do is you just like look at pre-existing data, like scour the internet. Because I'm building this one from scratch and I don't know of anyone with the exact same hardware design that I do, I'm probably going to have to collect all my data. There's no pre-existing data. And one thing to always keep in mind is if you want more data, your algorithm's going to be better, but it's going to cost more money and more time. So if you want a lot of data, you have to come up with the data collection procedure. If you want other people to collect data for you, you need to teach them the procedure. There's training. You need to manage these people. You have to do QA. You have to coach them. It's a lot of work. Cool, so we've decided for this project that I'm going to be the only data collector. And this is fun because we finally start to get to build stuff. So yes, now we're going to start coding. The important part of this is with IMUs, whatever gestures you're going to be using is highly dependent on your mechanical design. And if you change your mechanical design to a large extent, you're going to have to recollect all your data from scratch. So before you start data collection, it's a good time to lock down your mechanical design. And the next important thing to do when collecting data is making sure that you record data for all your expected use cases. So this is who is going to be doing the gestures, what posture are they going to be using, so are they left-handed, are they right-handed, when are they going to be doing this, where are they going to be doing this. Fortunately, earlier when we were defining our problem, we already answered this. So for this project, you have to collect data in all of these categories. So you want the gesture to work when you're sitting on your couch. You want it to work sitting in your chair. You want it to work sitting on the floor. You want it to work when you're standing. You want it to work when you're walking. And because we have this matrix, you can see that quickly you start to have to collect a lot of data, even for a very small project. And I'd like to add a note for negative data. So negative data is collecting data where there's no gesture at all. And for this, you have to think about all the situations, all the data that you could generate when you're not doing a gesture. It isn't just standing there. So for me, I'm like, what are the things that I do in my day-to-day life where I don't want there to be a gesture? Well, I don't want there to be a gesture when I'm like standing up or sitting down, walking around, turning to face someone else. So I have to collect data for all of this. And then you have to be like, what are all of my weird quirks? So for me, like, I like to jump up and down a lot when I'm excited. So I have to record a lot of data where I jump up and down. I like to do this when I'm excited. So I have to record data of myself doing that over and over again. So negative data is pretty important to cover, and you just have to think a lot about all the situations in your life. Do some like self-introspection. Cool. And the next thing about data collection is it's an exercise in diligence. You have to like keep really good notes. If you've ever kept a lab notebook before, it kind of feels like that. So this is a picture of me where I just have a Google spreadsheet and I have a list of all of my data. And then on the right, I have visualizations of all my data, and I just manually inspect it piece by piece. So this just takes a lot of time and patience. And you're always like, is there some beautiful library that will do this for me? And often, like, Google Sheets works pretty well. Okay, so now we're at the point where I've written my collect data Python script. It's on my GitHub, so you can just use it. Hooray! It spits out all my data in CSVs. And for this project, I ended up recording about 286 1.5 second traces. So a trace is like a recording of sensor data. I used 98 Wingardium, 99 Flipendo, and 89 negative traces. And if you want to like downplay how much data you collected, you can be like, oh, I spent all of this time collecting 7 minutes of data. But if you're pitching to an investor about like how awesome your project is, you can be like, I collected over 250,000 data points. So it's all about what units you use. Cool. We finally done all the work, been super diligent, collected the data. Now we're going to start training our model and iterating on our model. Cool. So it's a lot of data cleaning. Again, the theme of machine learning is you just need a lot of diligence. You do a lot of this exploration in Jupyter Notebook, and you can take a look at my notebook in explorations that whatever the extension is. Just take a look. It's really nice just kind of going and just looking at the data. So when you're training your model, the first step that you want to do is you just look at the data that you've gotten out. So in this picture, the top one is the top row is accelerometer. The bottom row is a gyroscope, and there are 3 lines on each plot because all the sensors are XYZ. So each line is XYZ. And the first thing you want to do is you're like, okay, I'm doing traditional machine learning. At the end of the day, there's not a lot of magic going in. So to get an estimate of how hard it is going to be to get my algorithm, I just visually inspect the traces. So how different is the Wingardium column to the Flipendo column? And you stare at this and you're like, they're like surprisingly similar. Like maybe this will be difficult. But yeah, I've already kind of defined the problem, and it's now like 2 weeks from Halloween, so maybe I'll just have to go and like see how far I get. Cool. So we're like, okay, well, I don't want to think about things, so I'm going to just create some like very boring features. So again, look at the sensor data that we collected earlier. So for each like sliver of sensor data, I'm just going to record the maximum accelerometer signal, the minimum, the range, the mean, the standard deviation. I'm going to do the same for the gyroscope. So these are the features that I'm going to be dumping into scikit-learn. And let's see how well we do. So first iteration, I collected 102 traces at that point. It didn't work well. What do? Collect more data. Awesome. Iteration 2, it still didn't work well. I had 167 traces. What happened? I decided to clean the data and collect new data. Iteration 3, I've now collected 286 traces. It works okay. The problem is it doesn't distinguish like the Flipendo from the Wingardium very well, which we kind of guessed would happen based upon the graphs that we saw earlier. So now this is when we get into our domain specialized knowledge. Now we're going to look at some feature design that we can do. So I'm going to go back to this graph and I'm going to be like, like how is Wingardium different from Flipendo? Like they look very similar. Like what am I going to do? So I stared at it for a while, and the first thing I noticed was If you look on the right, Flipendo has this like third peak in the accelerometer z-axis. So I'm like, cool, this seems promising. There are 3 peaks for Flipendo and 2 peaks for Wingardium. Awesome, like maybe I'll get somewhere here. Unfortunately, it is now like a few days before Halloween, and I'm like, quickly, how do I count the number of peaks? And one thing that you'll learn if you go into like peak counting is it's actually not an easy problem. It's like an area of research that's going on. So I'm like, okay, what can I hack together really quickly? I hacked a 75% accurate peak counter. So now whenever I dump in sensor data, it'll have a 75% chance of telling me how many peaks there are. Cool. Sorry, it'll always tell me the number of peaks, but it'll only be right 75% of the time. So these were my original features, and I add this last feature, which is how many peaks are there in the accelerometer z-axis. Cool, now that I've done this feature design, I'm on my iteration 4, and I'm like, well, it's Halloween, it's good enough, it's time to ship it. All right, awesome, I'm shipping it. And because it's also pretty close to Halloween, now I just need to, now I have this model, I need to start productionizing it. And I also need battery for my laptop. Cool. All right, so it's Halloween. I get my costume. I go out, I'm Harry Potter. And I dump my model into this Python script called gesturedetector.py. It's actually surprisingly easy, because what happens is scikit-learn, it'll give you a file, which is like a model. So it's just a single variable called model, and then you can be like, okay, I will call a function called classify, and the output of this will be, is there, what gesture is there? And Python has this awesome thing called pickling. So it's basically like take this Python object and save it in some sort of format. So you just pickle the model that you get, and then you load it in gesturedetector.py. You make your loop that runs forever, and you have your gesture detector. Because it's already Halloween, you may or may not, I didn't do a little or a lot of tuning, but if you want to do this for real, you probably need closer to a lot of tuning. Cool. So now we've gone over the 5 steps that you have to do when you're doing gesture recognition. So you have to define and scope your problem. You have to propose your model and algorithm. You have to collect the data. You have to train your model and iterate. And finally, you have to productionize the model. But we've gone through all the steps. We built our one. This is super exciting. This is magic. And lastly, I would like to encourage you, you can use these steps to build even more stuff. So let's talk about even more stuff that you can use. So IMUs and machine learning really introduce a lot of magic when you start to do them on a large scale. And this is why I love sensors so much. So one example of a thing that you can do is you can sense whether someone is walking or not based upon a wearable that they're wearing or their phone. And once you can start sensing this, you can actually measure the walkability of different cities. And then you can start using this for urban planning. You can, I don't know, if you're a researcher, you can really start working with the city planners being like, hey, you planned your city this way, and it's now this walkable, and now people are this healthy. You can have better health phenotypes because you can start detecting when are people running, when are people hiking. It's really, really exciting. Next, you can start looking at depression treatments because one of the things you can measure are people's heart rates when they're sleeping. And you can be like, is this person sleeping well? And you can because you have a large population, you can be like, okay, they've received this medication, they're sleeping well. This other person has received this other medication, they're not sleeping well. So you can really start to look at all these different depression treatments. Another interesting application is census data. So especially if you're in the developing world, it takes a lot of investment and money to go door to door to see how many people are in a particular region. But mobile phones are really popular in the developing world. So if you just look at what data is coming off people's mobile phones, you can suddenly get a really, really accurate census of all the people in that country and where are they living. And you don't know the areas where people don't have phones, but it's surprisingly ubiquitous. I think there's a researcher at Berkeley who's working on this. And a final thing that I'd like to talk about is earthquake detection. So typically, if you have a bunch of phones or sensors on a table, they can measure shaking. And basically, an earthquake is happening if you have a lot of phones on tables that are suddenly shaking in a particular place. And earthquakes generally happen in 2 waves. So if you can detect the first wave and alert people, then you can tell them to leave before the second wave wave of shaking happen. So it's like really exciting. You can use the exact same steps that I talked about earlier to start to have these large scale research problems come to fruition. But you can also like build your firebending gloves or your like steel ATM pins or music control gloves. There's a lot of stuff that you can do both on a large scale and a small scale. So yeah, here are your steps. Go forth, build lots of cool stuff, and I would be super happy if you told me about it. That's my email address. Cool. All right. Thank you so much, everyone. Oh, I should see if this works. There's sometimes, this is the tuning part, and live demos often don't work. Let's see if this works. Nope, it's not working. Yeah, come find me afterward. There's some time to set up, and hopefully because we're not running live, the live demo gods will be not present when I try. Cool.